Okay, hello everyone and welcome to calculus. This is the start of the actual calculus portion of the class. We are going to be talking today about section 1.4, which is the tangent and velocity problems. It's kind of amazing how one really simple concept that goes back to geometry is going to really be a key to everything that we're going to be doing pretty much from here all the way through the end of calculus. It doesn't mean that every single piece is going to have this in it, but this is really the basis. It's kind of where it starts. So our outcome today is to develop the idea of a limit. Now, if we were in class, we would have a huge discussion about what a limit is, just in everyday terms. Most of the time, people think of things like, well, there's a speed limit. Okay, so let's use the idea of a speed limit and actually start there. We know that there's a speed limit, and the speed limit is something which can not only be attained, it can be exceeded, and unfortunately often is. Most people, if you see the speed limit is 55, they tend to go a little bit faster than 55. So not only can you attain that limit, you can surpass it. You can actually reach and be exactly at that speed limit. So that's one idea of a limit. A lot of other people think of a limit of something that you can't necessarily attain. And probably a good, I would say a good idea for this, think about, and for those of you guys who are non-sports people, hopefully you can still pick up on this. Think about the fastest runner in the world. At least up until very recently, it was Usain Bolt. He was the fastest sprinter for the 100-meter dash. And if I'm not mistaken, he did the 100-meter dash in 9 point something seconds. I could be wrong about that. There was one time that nobody ever thought that we would break the 10-second mark for the 100-meter dash, but that has been broken. It's gotten down to 9 point something. If you really think about it, there's probably a good chance that somebody someday will probably break the 9-second mark and run the 100-meter dash in just under 9 seconds. There is more than likely, however, a time between 0 and 9 seconds that physically can never be broken. You know, maybe it's 6 seconds, although I think that that's probably a little low, but there's probably a limit to the time that just cannot be reached. It cannot be broken. So that is also the idea of a limit. Now we're going to start to define limits more using calculus and algebraically and conceptually and numerically and all these different things. So just know that there are ways that sometimes you can reach a limit and even surpass it, and then sometimes there just is a way not to reach a limit whatsoever. And you may come up with a whole bunch of other ideas on your own, but that's the general concept. So let's talk about the structure of calculus. Calculus starts with this whole thing, which is called limits, and then limits branch off into two other main topics, integrals and derivatives. And then once we're done with that in these courses, if you go on to calculus BC, you will also see series and sequences, which really incorporates both integrals and limits. So no matter which course you're taking, you will see at least the branches that you see here: limits, integrals, and derivatives. Okay. So the first thing is, and you see a little circle at the bottom of your page, what I normally have people do when we have a little bit of time is I tell you to draw and label a tangent line and a secant line on the above circle. And then we kind of talk about what the difference between the two lines is. So I'm going to give you a few seconds here just to go ahead and sketch what you think a tangent line would look like and sketch what you think a secant line would look like. I'm still waiting. Okay, more than likely, if you had somewhat of an idea, you've already sketched it. If you didn't have an idea, you might be trying to think about it. What is a tangent line? What's a secant line? Most of us remember tangent line. A tangent line might look something like this, and you could have drawn it in a whole bunch of different places, but a tangent line might look something... Whoops, that is a bad tangent line. Let me redraw that. tangent line might look something like that. And what you should notice is that my tangent line, basically it hits the outside of the circle. It really only hits the circle at one specific point, whereas a secant line goes through the circle and hits the circle, in this case, at two different points. Does not have to go through the center. Mine looks like maybe it did, but it does not have to go through the center. I could have drawn a secant line out here. That's also a secant line. It goes through the circle at two different points. So that's really the differences between a tangent line and a secant line. So we'll say the tangent line hits the curve, in this case our curve was a circle, at only one point. And then we'll say our secant line hits the curve at 2 points. And that's really the general idea behind those two things. This is stuff that you might maybe goes back to geometry. I'm not sure if you would have seen it in some other class, but that's pretty much it. Tangent line hits 1 point, secant line hits 2 points. That's really the basis of how we're going to start to define limits. All right, so the idea of a limit. The idea of a limit is used in the tangent line problem. Finding the tangent line to a specific point, so to a point, is equivalent to finding the slope of the tangent line at that point. And so to approximate this, what we're going to do is we're going to use the slope. So to approximate this slope, we're going to use secant lines. Rewrite that does not look good. Secant lines. All right, so here is our example, and hopefully this will make sense to you. First of all, we're going to start off with the equation of the tangent line. Sorry, we're going to find the equation of the tangent line to the parabola y equals x squared at the point 2, 4. So the first thing we need to do is we need to sketch what y equals x squared looks like. Hopefully you remember that just basically looks like your general parabola opening up, and it's got its vertex at the origin. So in order to do this one at least semi-correctly, I'm going to sketch little tick lines down here. 1, 2, 3, 4. 1, 2, 3, 4. I went 4 out in each direction, trying to keep them relatively close to being the same distance apart. Not easy to do. And then I'll go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That should be good enough. The only reason I knew I went up to 16 is because if I go out to 4, I'm going to go up to 16 on my graph. And if you didn't follow that, let's go ahead and sketch this. So let's actually sketch the graph. So we know that there's a point at 0, 0. That's where the vertex is. So to find the other points, I'm just going to take nice, easy whole numbers so I can get a sketch. If I take x as 1, plug it into y equals x squared, I get y as 1. So we've got a point right there. If I take x as 2, plug it in, I'm going to get y as 4. So that looks like 2, 1, 2, 3, 4 is about right there. Doing our best to sketch this thing. If x is 3, y is 9. 6, 7, 8, 9. So it looks like it's going to be right about here. And then if x is 4, it's going to be up to 16, which I believe was my top tick mark. So the way I drew this, you're not really seeing the curve all that exceptionally well, but it is actually a parabola. And when I sketch it in there, I will do my best to sketch this thing in there so it looks like it is curving. And then it mirrors on the other side. I'm not so worried about the other side because I'm not going to be using that one as much. But there's your parabola. And if you have not had me before, you'll hear me say this at some other time. If for some reason your sketch is not good enough, like mine isn't, and it actually does not hit the dot, the fix to that, the trick is to make the dot bigger. Now it works. Now it works. Make my dots bigger. Over exaggerate them. There we go. Okay. So now we have our points that created the parabola. So now we can go ahead and take a look at what's happening. Well, in order to find the slope of any line, no matter what the line is, you should remember you need 2 points. We have to have 2 points to find the slope of a line. Well, let's say, I'm going to go ahead and draw another dot right down there at -1, 1. Let's say that I wanted to find the slope of the tangent line that hits 2, 4. So the first thing I'm going to do is I'm just going to sketch that tangent line. So let's see, the point 2, 4 is right here. I want to sketch a tangent line, which means it can only hit the curve once. So I'm going to kind of try and do this by sketching it that way and then sketching it that way. And you can kind of see, again, I'm going to make my dot a little bigger because I didn't really hit my line like I should have. You can see how that's going to only hit the outside of that parabola at 1 point. Assuming it was exactly correct, it would actually be up against the actual parabola. I kind of missed. You guys will have probably an easier time to do this with your pencils and papers. Okay, so there we have our tangent line. Now the problem is, the tangent line, if I want to find the slope at this particular point right there, we're going to call that point P, because that's what it is. That's the point 2, 4. Well, in order for me to find the slope of that parabola at that point, I would need another point on the parabola. But the problem is that point is not also on the tangent line. Or I would need another point on the tangent line, and then that would also tell me the slope. Because here's the thing. If I were to know this point on the tangent line, I could then find the slope between 2, 4 and the red point up here. And whatever that slope is, because it's a line, it's the same slope everywhere, which means that it would be the same slope as I would have here. It would be the same slope as here. It would be the same slope as here. And lo and behold, it would be the same slope as here. And since that's where the line hits the actual parabola, that parabola has that exact same slope as the tangent line. But the problem is we don't know any other points on the line. We don't even know the equation of that tangent line at this point. That's what we're trying to find. So how are we going to develop that? Well, here's the idea. We are going to take a secant line through any one of these other blue points. Technically, it doesn't even have to be the blue point. It's just that those are easier to deal with. I'm going to draw a secant line from the point -1, 1 through my point 2, 4. I'm going to dash that point. Dash that line so that we can kind of see that this is not really the line that we're looking for. We're looking for the tangent line, but that's a secant line. Well, now I can find the slope of that purple dotted line. That I can do. Because that's just going to be taking the point, and we're going to call this other point right over here, Q. That's the point -1, 1. We can find the slope between 2 points. That's just your basic y2 minus y1 over x2 minus x1. So in this case, we'll have y2 minus y1, which is 1 minus 4, over x2, which is -1, minus x1, which is 2. So we're going to get 1 minus 4 is -3 over -3. And simplifying, that's 1. So my slope between Q and P is 1. So the real question is, well, is that a good approximation for our tangent line slope? Well, you can clearly look at the purple dotted line and the orange line. Those things are not really that close together. Is it an approximation? Yes, it is an approximation. It's just not a very good one. So what can we do? Well, what we're going to do is we're going to take and we are going to move our Q value closer to P. So now I'm going to take 0, 0, and now I'm going to draw a secant line from 0, 0 through 2, 4. Again, I'm going to dash it just so that we can see. That's the secant line right there. So my new point Q is the point 0, 0. So now we've taken Q and we moved it closer. Again, I can do a quick little y2 minus y1 over x2 minus x1. And we're going to get 0 minus 4. That is a minus 4 over 0 minus 2, which is negative 4 over negative 2. Whoops. Come on. Draw there for me. So that's going to reduce to 2. Well, that is now my slope. That's my m. That's my slope. Again, it's not the best approximation. It is an approximation, but it's getting better. And hopefully you can see that the idea is let's keep moving that point Q closer and closer, and let's just see how close we can get. I'm going to have to do a little bit of scrolling here. So now let's try, I haven't done a black one yet. Let's do one in black. Let's try it from 1, 1 up through 2, 4. So now I'm going to go ahead and again, I'm going to dash that. And again, hopefully what you can see is it's not the best approximation, but it's getting closer. So now we went to the point 1, 1. And let's do a slope. So that's going to be 1 minus 4 over 1 minus 2. So we get negative 3 over negative 1, which is 3. Okay, we're getting a higher slope as we go, which makes sense because the slope that we want is steeper than these ones that we're approximating. So it does make sense. Well, you might look at this and think, well, wait a minute, I've just kind of run out of points. The next point is 2, 4. Well, technically, you could go in between. We don't have to just use the whole numbers, although they were easier. So now let's go ahead and maybe do, I'm not going to draw this one just because it'll be too difficult to draw, and it's too messy on that graph above. Let's do the x value of 1.5. And the question might be, well, what's the y value? Well, remember, 1.5 is the x. The equation was y equals x squared. So we'll just plug 1.5 in for x. If you square 1.5, you get 2.25. 2.25. One other thing you will find is I am very, very big on mental math. So the better you are with multiplication stuff and mental mathematics, the easier this stuff is going to be for you guys. All right, so let's go ahead and do the y2 minus y1, which is 2.25 minus 4 over 1.5 minus 2. And that's going to give us, what is that? 2.25 minus 4 is negative 1.75 over negative 0.5. And I believe that's 3.5. It's okay if you couldn't quite do that one in your head. That's fine. You might be able to kind of guess what this slope looks like it's going to be, but we'll eventually get to the actual answer. In general, what I can do is I can start taking this Q value and I can start moving the Q value closer and closer and closer and closer and closer until I get almost right up to P. I can't actually make it P because then if you make the actual point P, you've got two of the same point and you'll end up with an undefined value, so that won't work. But I can make it really close to P. As a matter of fact, I can pick any X value that I want to other than 2. So that's what's in this last box right here. It's saying that if I pick any X value, the Y value that I get out of it is going to be X squared. So any Y2 minus Y1 is going to, well, Y2 here is X squared. So that's X squared minus Y1, which is 4, over X2, which is X, minus the Y value, which is 2. So basically, I've come up with a formula that's going to give me any slope that I want. So the idea here is, in order to get a better approximation for the slope of the tangent, we're going to use points which are closer to P. Okay? And we're going to see how all this stuff actually works out. We'll go to the next page here. So to find the slope, we're going to use the equation that we just came up with, which is x squared minus 4 over x minus 2. And we're going to talk about a little bit of notation here. So it appears that as x, and that arrow means approaches 2, then f of x approaches, and you might have already guessed that it looks like it might be approaching 4. So as q approached p on the previous page, it looks like the slopes of those secant lines, which is what this thing means, the slope of the secant line, approaches 4. So symbolically, what we can say is this LIM is called limit. It says the limit as q approaches p, that's what this part is, the limit as q approaches p, of the secant slope of the line segment between p and q approaches m, and we're actually going to write m sub tangent, because what's happening is the slopes of the secant lines are getting so close together that once they get infinitely close together to the point where you can't even tell the difference, the slopes of those secant lines become the tangent line slope. So you take the limit as q gets closer and closer to p, and what you're going to end up with is the tangent line slope. So in our example, what we had was the limit as x approached 2, because that was the x value of the point that we were interested in, of x squared minus 4 over x minus 2 appears like it is approaching 4. All right, that is enough for video 1. We're going to come back in video 2, and we're going to finish this off. I'm going to show this idea in general, and then we're going to go through some numeric and real-life examples.